To demonstrate simple linear regression and multiple linear regression in Python, we will need a dataset. So I'll point to this resource. It's the bike sharing dataset available from UCL Machine Learning Repository. So the UCL Machine Learning Repository is a very famous repository which has like tons of datasets available for different use cases. So as you can see, we have a variety of datasets available for classification, regression, clustering, and probably for different categories, we have several other datasets. So I'll request you to open up regression. Within regression, you will see there are various datasets available. I'll point you to the bike sharing dataset. And if you open up this in a new tab, you can see it will give you basic information about the source, dataset information, and the attribute information. So this dataset is about a bike sharing company. A bike sharing company generally allows you to rent a bike and help you travel from point A to point B. So let's say you're traveling from point A to point B, you can rent a bike at point A, travel to point B with the bike, and then drop your bike at point B and then move on to your forward journey. So the bike company would actually have an inventory of, let's say, around 1,000 to 5,000 different bikes, and based on the demand, they might increase it or decrease it. And the demand might be defined by whether it's a working day, whether it's a weekday, if it's a holiday. The seasonal attributes might have an impact on the sales. So in the data set, you have three variables towards the end: casual, registered, and count. Count gives you the total number of rental bikes, including both casual and registered users. And casual and registered gives you a split that adds up to count. So this is the total number of casual users who have rented the bike for that particular day, and this is the total number of registered users who have rented the bike for that particular day. Then you have a couple of weather information, a couple of other flags, and so on. There are two datasets available. One is at a day level, and the other one is at an hour level. So I'll request you to download this and import the day level CSV file into Python Spider. So let's move on to Spider. So I've already downloaded the dataset. So let's import a couple of important packages that we will need for this exercise. So I'll import pandas we'll also import matplotlib because we might need some basic uh, visualization in this exercise. We'll say matplotlib.pyplot as plt, and we'll say df is equal to, we'll import the day level file, so pd.readcsv, and we'll say day.csv. So here we have the dataset imported, and let's do a simple overview. So we'll do df.shape, and we can see that there are 731 rows and 16 columns. We'll do df.columns to see what columns do we have in the dataset, and as you can see, we have the date information, seasonal, year, and month information, flags for holiday, and just as we saw over there, we have all these variables in the same order. So let's do a simple df head and see what dataset actually goes into it. Here we go. So you can see count has numbers ranging from something like 500, 1500. Then we have weather attributes, the numbers for registered and casual users, the date, and so on. A couple of other, yeah, we have the date and a couple of flags. So that's the dataset looks nice. Now let's define the use case we're trying to solve. So we're trying to solve, let's say we're trying to solve the total count or the sales as a function of an independent variable in this scenario, which is, let's say, temperature. So we're saying that for a particular day, the total number of sales, which is the total number of bike sharing deals that have happened, can be defined as a function for the temperature of that particular day. Let's say the average temperature for that particular day. But this is a simple use case where we can define simple linear regression. So we have an independent variable, which is the temperature. We have a dependent variable, which is sales, and to be specific in this scenario, count. And you're saying y is equal to mx plus c, where m is the impact of x and y, x is the independent variable, which is temperature, y is the independent variable, which is y is the dependent variable, sales, x is the independent variable, that's temperature, and C will be the intercept. Now, to perform linear regression, we will need to import the linear regression function available from sklearn. So if you do from sklearn.linear model import linear regression, it will import the linear regression function into memory. I'll create a new object called lm, which will be the linear regression object. And let's create one. There we go. So we have lm, which is a linear regression object. So how sklearn provides the linear regression function is we'll have two functions within linear regression object, which is one would be a fit and the second would be, let's say, predict, to be simple. Fit is a function where you can provide the x and y variables along with a couple of extra parameters, and then you can allow the linear regression model to fit the line. So it will technically find the best fit line that fits across all the points that you have provided. Predict is basically done after you fit. So once you have fit, you have the linear regression object that has learned the parameters. So in the case of y is equal to mx plus c, it knows the values for m and it knows the values for c. And using that object, which is lm, which is now fit, you can do a predict, and you can just say, you can pass in the value and give it the predicted output for that particular uh, input. So let's try doing a simple linear regression over here. So I'll say simple linear regression object, which is lm dot fit. Now, if you see over here, we have x and y variables to be passed. So the x would be over here, df, and we will say temperature. That is the x. And y would be df and cmt. This is the y variable. Now, there's only one cosmetic change that we would need to do. We would need to reshape the shape as, I'll just explain what I'm doing over here. Now, if you pass just one column over here, the shape which goes into it is a little different. So let's say if you're doing df 10 dot shape, you see that it's 731 values. But then if you reshape it into -1, 1, and then you do a shape, you can actually see that it's 731, 1. So the definition becomes clear, and linear regression objects expect inputs with a defined shape. So just define them. So had it been a scenario where you have passing for a multiple linear regression use case, so you'll be passing, let's say, 5 variables as an independent variable. So in that case, it will have a proper shape. It will have a shape like, let's say, 731 into 5. That's fine. But when you're passing a single variable over here, it's getting passed as a series, and it doesn't have a definite shape, which is not acceptable for the linear regression object. So now this is defined, let's just run this function which creates a linear regression object. So it has now created a linear regression object and it has fit the values which is now required for which is now the best line that fits through all these points for x and y. So we can do a simple predict, but before that, let's look at the kind of values which we have for our parameters over here. So if you do lm dot, and you can see what all objects we have, we'll say intercept. And you can see the intercept is a value which is at 1214. And if you do lm dot parameters, in fact, let's just call this simple predict function, and then we'll come back to this. So lm now has the equation. We'll just say let's pass the value of temperature as 0.45. What does it predict? It predicts that there are around 4,200 sales that is expected. And if you pass something like, let's say, 15, it's the sales expected is around 2,200. So it's kind of a linearly increasing trend. You can actually figure out that the line would be kind of an increasing line over here. Now, if you just do a simple plot to understand how does it look, so let's say you do plt dot scatter, and the first variable you pass is, let's say, the x1, which will be temperature, and then you pass df dot count. You kind of understand that this is an increasing trend. The line which would have been predicted as the best line would be somewhere like this, and it will have a slope and a definite intercept. And based on that intercepted line, we're getting this value for the predict function when you're passing the value of 0.15. Now, when we saw the intercept, we have the value for the c variable in this equation y is equal to mx plus c. Similarly, we can also do coefficients. We'll say mm dot coefficients, and we get the value for the coefficients. So in this scenario, we just have one simple value for the coefficient, which is m. That's 6640. So that's how the value for uh, the slope has been calculated. Now, if you just reformat this equation, we can write it as y is equal to 6640.7 into x plus c, and c would be 1214, as we can see over here, 1214. That's the intercept. So that's how the equation is getting constructed. And when you're calling the predict function on the ln linear regression object, and you're passing the x over here, it's fitting in this x into this equation where it already has m and c, and it is giving it respective y. So that's a very simple example to understand linear regression, simple linear regression, where you have one dependent variable and one independent variable. Now, if you make this example a little more extended one, where we have multiple independent variables and one dependent variable, that's the case for multiple linear regression. It's exactly the same. You just have one extra extension to it. We can create a linear regression object. So if you just redefine, let's open the columns again. So we'll say, now if you look at the columns, we have count as your y variable, which is a dependent variable, and you're defining your dependent variable as a function of temperature, humidity, and let's say another variable like holiday. Or in fact, just let's keep it simple. We'll keep just temperature and humidity, right? Now, what we do is we'll say we use the same function. Let's say ln dot fit, and we pass the x. X would be over here, a data frame, and in this data frame we pass two variables, two columns. So we'll create a list. The first one would be temperature. Second would be humidity. So we have two columns in this data frame. So the shape of this one would be around 700 rows into 2. And then we pass the y, which is df dot count. And let's reshape this. There we go. Now I will create a simple object where we have it. So we have linear regression model, which is fit with a simple equation that predicts count as a function of temperature and humidity. And now if you repeat the same process, let's have a look at what values do we have over here. So we have lm of intercept as 2657, and the coefficient as we have two coefficients. So we have one for temperature and one for humidity. So as you can see, this is a negative value, which means that we have a negative impact from humidity. So we will do the same scatter plot with humidity. Let's have a look at that. Now, instead of temperature, let's pass humidity. It's kind of a decreasing trend, but this is the trend. So as humidity increases, sales kind of goes down. This is the trend you can see over here. Now, if you combine this into this equation, so let's say now we have this would be interpreted as y is equal to m1 x1 plus m2 x2 plus c. So m1 would be the coefficient of x1. x1 is temperature, so m1 would be 6886.97. m2 would be the coefficient for humidity, which would be minus 2492.85. And c would be the intercept. Intercept in this scenario was around 2657. So if you look at the overall equation, we can see that the intercept has changed compared to the previous example when we just had one simple variable. And you see that this will change as you add more number of variables. So a significantly different, more and more attributes help you to understand the relationship in a better way. So explain more part of y with a couple of x variables. So the more number of variables you'll have, the more strong your relationship will be, and you'll have more accurate results. So this is the new equation where we have y as a function of x1 and x2. Now, if you do the same predict function, so let's say we can just take a few values from here. So let's say we have, just to get an idea of how it looks like, we say a head of this one, the two columns in Regression, and we can see that approximately we have humidity from 0 to 1 is a normalized value, and the same is the case for temperature. So we'll pass a simple value over here as an array. We'll use the predict function again. We'll say lm.predict, and we'll pass the two values, let's say 0.34 and 0.55, and we call the predict function. It'll use the equation and give you the output that around 3628.39 sales are expected for this situation. So this is an example for multiple linear regression. Now, just for a recap, we've looked into supervised machine learning algorithms, then we talked about regression. We've understood what is regression. Regression is a technique that determines the relationship between one or more independent variables and a dependent variable. Now, based on few academic textbooks, we have different calling styles for the dependent and independent variable. We sometimes call them target of input, target of input, or criterion and Pareto variables. Now, linear regression, we looked into simple linear regression and multiple linear regression. The difference between them is simple linear regression will have only one independent variable, and multiple linear regression will have two or more independent variables. We've delved into the depth of simple linear regression by understanding how is a line fit and defined as the best fit for all the points between x and y. We understand how we construct the equation for a simple linear regression equation, that is y is equal to mx plus c. We looked into little extra details that why can't we just use correlation and what is the best way to find the best fit line. Now we moved on to understand multiple linear regression, and we can just extend simple linear regression to include several other independent attributes and create a simple equation as y is equal to m0 plus m1x1 and so on up to mnxn, where n is the total number of independent variables. And each of these, m1, m2, is the individual impact of the variables corresponding to x1, x2, and so on. And then finally, we looked into a simple Python-based demonstration to understand simple linear regression and multiple linear regression by leveraging the bike-sharing dataset available from UCL Machine Learning Repository. Let's move on to the next topic, and that is supervised machine learning for classification.